I'm going to take you quickly through what's been happening on the modeling update. Um, I think there's a big team. I've not managed to put all the photos yet, but there are 2 or 3 more photos that need to be added. Uh, Vivek is not today, but Rohit, the other team member, is on call today. So he'll also cover some sections as we speak. Rohit, you can pitch in as you see deem fit.
Yeah, please go ahead. I'll pitch in wherever required.
A lot of support. Like I said, there's been a ThoughtWorks volunteer effort as well on this. Then there's been Arka, who's also been a key supporter along with many others. Okay, so the modeling effort has basically been started quite vigorously the last couple of weeks. And like all projects, it's hard because we have to take a certain basis of how we want to build the model or how do we perceive the model to be built. We've taken a model basis called as SEIR model, on which we have kind of enhanced its capability to make it more India specific. Our objective has been that this model has to have value in terms of being deployable, as well as it has to be providing operational support, on-ground support, or the best way it can be integrated to the medical requirements that are there. So there's been a constant engagement with Dr. Ajay, Dr. Ram, and so on this. And so we have a lot of close collaboration, and many of the requirements that they want, we discuss and we kind of work on that. Most important, of course, we have the data that needs to come from the on-ground testing plus what's given available to us. Not going to bore you with the mathematics, but this is to talk about the model very briefly. The model SEIR is basically what in epidemiology, they call it as a contain or the compartmentalized models. So what it means is if you take, let's say, the population of India and you are trying to study this particular disease, you kind of divide that whole population into these 4 compartments. And the way the disease progresses is governed by certain mathematical formulas. In this case, they're called as differential equations, which kind of determine how the disease spreads. The traditional model has a strong basis, but it, however, does not answer things like, for example, we had a lockdown in March, and then a lockdown has got extended now till the 4th of May. And because of the lockdown, you have certain benefits and so on. But this is to give you the foundation basis that we're using for the modeling. Some of the important parts of modeling is the model takes a lot of parameters that it requires. Some of these straightforward things are the population, which I spoke to you about. But the kind of things that are really important are the kind of the ones which are highlighted in blue. For a disease, one of the most critical metric is what we call as a transmission rate. You might have heard of this also as R naught. This kind of says the infection spreads how fast. So generally, if I say, let's say a value of, let's say 2 or a 2.2 or 2.3 or 3, it means if, let's say I had it with me right now, what is the transmission? 2 people, 3 people, example. Now, because this is something, there are changes that are happening on the ground before the lockdown, then after the lockdown, this particular rate has a potential to change because you either did positive interventions or in some cases, the interventions may not be working, both could happen. So you want to bring down this value as low as possible for the disease to vanish. Mortality rate, it implies, what are the chances that a person doesn't make it through this disease. And hospitalization rate, typically who gets into an hospital. Now the model, if you look at it, takes these parameters in a very one-time definition view. Whereas in our world, we would actually want to see interventions, a lockdown was done, and then certain interventions were taken. So is my disease spread reducing and so on? The model needs to factor these kind of configurations. So taking this into account, we've kind of done a modified version of the model. In a very simple way, I'll try to explain this. What you see here this is your cases that are happening. The different colors are actually talking about the people who are exposed to the disease, how many people are infectious, how many are hospitalized, and the red, of course, is the people, the fatalities. Now, traditional models just went and said, I have one intervention, I had a value of R naught, which was at this point. Because of this intervention, there is a reduction in the value of R naught, and hence things are improving a little bit, what people call as flattening the curve. Now, to do this, the model had to be broken up to address a couple of changes. I needed to permit multiple iterations or interventions, multiple interventions that could happen. So you could have the lockdown intervention here, you can have future interventions, or you can have very specific local interventions that have been factored. In Mumbai, there might be ongoing, there could be very specific interventions, there could be local lockdowns. Factoring that into the configuration of the model, into the parameters, was one critical piece. The second piece was we wanted to break the compartment into age bins. So we have kind of broken it up into 0 to 20, 20, 40, 40, 60, and 60 and above. The reason for that being generally 60 and above with a lot of other comorbidities have a larger health risk. So when you want to try to do insights or you want to give operational insights, you want to be able to break this up by the age bins. What you're seeing here is, I'll try to quickly show you a live version of this as well. So our model has been built, and this is what we call as the India SER model. Here, there are two parts. I want to talk about another important part. India is a very large country, and each state, each district, each ward, there's a lot happening on the ground. So while it makes sense to look at a very large India number, which you're kind of seeing an India model, which is on the bottom, it is very important for me to actually understand behavior of the model at a very granular level. For example, the last couple of days, we are focusing and trying to understand and see how this model is behaving in a place like Dharavi, which is inside Maharashtra, inside Mumbai district, and one of the wards within Mumbai. Now, what happens when you go into that is it becomes a lot more challenging because you're trying to address a very granular model, and that granular model rolls up into a larger India model. So this is kind of what we call as a network-based model. So we have multiple granular models that are running. So you could have a Mumbai model, like I spoke. You can even have a Dharavi model. You can have sub-granular models under each. And you can actually start rolling these up beyond and beyond. Okay, you can take it to an India model, or you can stop it at a district level, or you can take it at a state level. Let me show you a little bit of how this actually looks, and then we'll actually talk a little bit more about what else we have done. Just give me a second. All right. Can you see my screen? So over here, this is a live instance that's running. This is just for internal distribution. We don't publish this. But if this is the map of India, we're actually pulling this from one of the open sources of data that we have. And it gets updated about 2 or 3 times a day. But if I wanted to look at the Maharashtra specific model, what happens is it goes and picks up the data that is configured for this particular state. Within a few seconds, you should be seeing this updated for Maharashtra. Second. Today's Murphy is really having a play.
You could
I'll come back to this. Let it load up. Let me come back to this as you go ahead. So using this model, so basically now, like any model, there are multiple components of the model. You have a visualization, which you've kind of shown you. The base model, which we have factored in the capability for the piecewise flexibility of putting multiple interventions, age binning, and then certain conditions that we can apply on the model. The aggregation so that you can actually have granular models, and then it starts rolling up into the India or the district or the state model. The syncing is happening. And of course, we will have to work on the larger integration pipelines as we move further ahead.